Alright, let us continue with calculating concentration of H plus and also OH minus in solution of strong acid or strong base. Now let us look at example 2 here. There are two types of solution. The first one is nitric acid 0.15 molar. Second one is calcium hydroxide 0.01 molar. Now you were asked to calculate pH as well as H plus and also OH minus concentration, both solution. So how to solve this question? Now first look at the nitric acid solution. Okay, so if this nitric acid dissociate into its ion, you will get H plus and also NO3 minus. So clearly you can see this is H plus, so we can calculate. So this concentration would refer to H plus concentration, which is 0.15 molar. And how to calculate OH minus concentration? We have to use the Kw expression. So Kw 1 times 10 power negative 14 divide with 0.15, we can get the concentration of hydroxide ion. Okay, don't forget the unit because unit is very important in analytical chemistry. Okay, if you forgot unit, you'll be penalized in terms of marks. Now next is pH. So to calculate pH, we negative log H plus. So we negative log 0.15, we get 0.82. Okay, so this one is showing it's an acid solution. Okay, acidic 0.82. Now second solution is calcium hydroxide. Okay, similar to the nitric acid, we write the dissociation of calcium hydroxide into ions, which are calcium 2 plus and also hydroxide ion. Okay, now for this case, you have to balance the reactant side and also the product side. So the reactant have one calcium, so this one okay. Here we have 2 hydroxide, okay, OH2, so therefore we have to have 2 also in the product side, so we put 2 here in front. Now to calculate hydroxide, because clearly we can see hydroxide here, because it's referring to 2 hydroxide, so we have to times by 2, multiply by 2 to get the concentration of hydroxide. Okay, so it becomes 0.02 molar. Now to find H plus, we use Kw, we get 5 times 10 power negative 13 molar. And to find pH, okay, we use the expression pH plus POH equivalent to 14. So 14 minus POH, okay, here we negative log the OH, we get pH of 12.3, and this one is referring to basic condition, okay, calcium hydroxide. Alright, the third example here is barium hydroxide, and this is the concentration of barium hydroxide. Okay, you are asked to calculate concentration of hydrogen ion as well as hydroxide ion. Okay, again we write the dissociation of barium hydroxide solution. You get barium 2 plus and 2 hydroxide, okay, balance. Now given the molarity here, so this one would refer to hydroxide, okay, so times 2. So to find H plus, we use the Kw expression. So this is the H plus concentration. Don't forget the unit, okay, molarity. Okay, molarity. Alright, how do we measure pH? Okay, of course the most accurate method to measure pH would be using pH meter. Okay, you dip the rod, pH rod into the solution you want to measure, and it will display the digital value of pH of that particular solution. However, if we don't have pH meter, we can estimate, okay, the acidity or the basicity of a solution by using dye, and this dye we can get from plants. Okay, for example, red cabbage, okay, the purple color. Okay, so you cut the red cabbage, you boil it, you get a purple color solution. Okay, that is categorized as indicator. And then you put that colored red cabbage into different solution that you want to test, whether it's basic or acidic. Okay, for example, you have coffee solution, so you put that uh, um, red cabbage water inside coffee, and you see the color change. And you want to test detergent, for example, you put that red cabbage into detergent, you get that color. Okay, of course it's less precise than pH because you don't get the value, but you can get the estimation whether it belongs to the acid or basic um, item. Okay, normally if it's basic, you get bluish greenish color. If it's acidic, you get orange red color. Okay. Okay, so again, here pH, to get pH, you negative log the H plus O H3O plus concentration. If you want to get pOH, you negative log the hydroxide concentration. Okay, and the relationship Kw will be equivalent to the multiplication of hydroxide and also H plus concentration. And the value of Kw is 1 times 10 power negative 14, and pKw will be equivalent to pH plus pOH, equivalent to 14. Alright, these are the example of indicators that we have in the lab. Methyl violet, thymo blue, methyl orange, methyl red, bromothymo blue, phenolphthalein, alizarin yellow are. I'm sure you are very familiar with phenolphthalein because you have used this in the practicals class. Now, different indicator will have different color change range. Okay, for example, methyl violet, the color change will be in the acidic region. Sorry, about 0 to 1.8, and the color change is from yellow to violet. Okay, for experiment that you have conducted, okay, between strong acid and strong base, you will estimate the the end point pH will be neutral to basic. So therefore, this is a good indicator because it will change from colorless to pink when it reach the end point, and this is the range of pH change for phenolphthalein. Okay, about 8 to 10. And if you see here, thymo blue have two range. Okay, in the acidic region, it will change from red to yellow. In the basic region, it will change from yellow to blue. Now, selection of indicator very important for titration purposes or any analytical techniques. Now, moving on to strong acid and base. So these are the 7 strong acid that you have to memorize. Okay, so apart from this, when you see throughout the lecture unit, it will belong to the weak acid group. So the 7 strong acid would be hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, chlorous acid, and also sulfuric acid. And the most important characteristic of strong acids, they are strong electrolyte. Strong electrolyte means it ionizes completely in solution or in water. For example, you have nitric acid, aqueous form. You mix it with water. Okay, it completely ionizes into H3O plus ion and also NO3 minus ion. You will no longer have this in the solution. That's what it means by ionize completely. Now, for case of strong acid, it's the only source of H plus. Okay. However, if molarity of the acid is less than 1 times 10 power negative 6 molar, then we have to take into account the auto-ionization of water. For strong base, the one belongs to group 1 and group 2 are considered as strong ionic hydroxide. Okay, for example, sodium hydroxide from group 1, potassium hydroxide from group 1, calcium hydroxide from group 2 in the periodic table. Similar to strong acid, strong base will is also strong electrolyte, and they dissociate completely in solution. Okay, so the pOH, or to find pH, you have to use the initial molarity of the base, like what we have done previously. And again, stoichiometry means you have to make sure balance between the reactant side and product side. Next is weak acid. Okay, the difference between weak acid and strong acid. Weak acid, they only partially ionize. Means when you have this weak acid, okay, you put it, or you mix it with water, okay, you get H3O plus, A minus, and also the undissociate HA. That's why you see the arrow pointing both direction. For strong acid, the arrow would point one direction only, towards the product side. Okay, so therefore for weak acid, we write the expression using Ka. Okay, constant for weak acid. Okay, so product over reactant. Okay, why we don't consider H2O? Because it's liquid. Okay, in the expression we only consider aqueous. Now, how to calculate Ka if we are given pH for weak acid? Okay, or using Ka to calculate pH. Okay, now for weak acid, it's not as direct like strong acid, because because the case that it is partially ionized. Okay, so that's why we have to use Ka. Now, we can also calculate the percent of ionization, how much of the solution ionized. Okay, so this is the formula. Okay, we use the equilibrium concentration of H plus over the original concentration of the acid, okay, times 100. Later on we see example related to this. Now, if you look at this curve here, okay, logically you would think the higher the concentration, the higher of solution ionized. But it's not the case. So you see here, the higher the concentration, the lower the percent of ionization of the solution. Okay. So for example, acetic acid 0.05 molar. Okay, 2% is ionized. Okay, but higher concentration of acetic acid 0.15 molar, only 1% of acetic acid ionized in water or in solution. Now, to understand this better, we look at the following example here of nicotinic acid. So this is obviously weak acid because it's not one of the 7 strong acid that you need to memorize. So this nicotinic acid is a monoprotic acid. Okay, and this is the formula for nicotinic acid. The concentration of nicotinic acid is 0.012 molar, pH 3.35 at 25 degrees Celsius. The question are, what is the acid ionization constant, Ka, for nicotinic acid, and what is the degree of ionization of this nicotinic acid in solution? So 2 questions being asked here. So how to solve this question? Alright, how to solve this question? We can abbreviate because it's only referring to a monoprotic weak acid. So mono means only one ionizable proton. So H and IC, this one refer to nicotinic acid. Okay, so writing the dissociation of nicotinic acid, you get H plus and also NiC minus. So this is a ice table that you need to draw to solve question like this. Okay, so I call this ice table. Okay, I initial, this one is our starting, C change, E equilibrium. So we are given the initial concentration of nicotinic acid, which is 0.012, and initially none of this present. Okay, none of this have dissociated yet, so 0, 0. Okay, during the dissociation process means some of these would decrease, so you get negative X, forming H plus and NiC. That's why you get plus sign here, plus. And at equilibrium, we just add initial plus change, so you get 0.012 minus X, 0 plus X, X, 0 plus X, X. Okay, now we put this equilibrium into the Ka expression. Ka, get acid dissociation constant for nicotinic acid, multiplication of the product over initial concentration. So here X squared, okay, X times X squared, divide with 0.012 minus X. Okay, so question is asking for you to calculate Ka. Remember, you are given pH. So pH is actually referring to H plus. When you negative log H plus, you get pH. So you anti-log pH, you get H plus concentration. Okay, so on your calculator, you have to press the shift button first, and then you press log. Okay, that's for anti-log. So you get 0.00041 molar. So you substitute this into this expression here, okay, because this is the X value. You put it here, you put it here. Okay, the step is not shown here. They only show you 0.012 minus 0 minus X value, which is 0.01159. So you substitute it in the expression. Okay, 0.00041 squared divide with 0.01159, you should get 1.45 times 10 power of negative 5 Ka value. So Ka value no unit. Okay, second question, percent of ionization. The formula, how to calculate percent ionization, H plus at equilibrium divide with original concentration times 100. Okay, so 0.00041 divide with 0.012 times 100, you should get around 3.4%. That is percent of ionization. So only 3.4% ionized into H plus and NiC minus, and the rest remain as H and IC. Okay, the next example is vinegar. Okay, vinegar is example of weak acid, and the pH of vinegar is 3. Okay, so given Ka for acetic acid, because vinegar is made of acetic acid, this is the Ka value for acetic acid. Calculate the concentration of acetic acid in vinegar. So how to solve this question? Okay, again, ice table. Okay, draw the ice table. Okay, acetic acid formula. If you don't know the formula for acetic acid, you can abbreviate because it's monoprotic weak acid. Okay, like nicotinic acid just now. So this is the formula for acetic acid, CH3COOH plus H2O dissociate into CH3COO minus and H3O plus. Okay, so this is the ice table. The initial, which we don't know. Okay, and we know it depleted, so X minus Y. We cannot use X because we have put X here, so we use Y. So minus Y. So this one is plus y, okay. However, we are given the pH, okay. So pH, you antilog to get the H plus concentration, which is 1 times 10 negative 3 molar. So we substitute this value of y into the Ka expression here, Ka expression, okay. And then you are given Ka value, so substitute the Ka value, okay. From there we should be able to solve the initial concentration here, X, of acetic acid. In this case is 0.056 molar. Alright, the next example, weak acid having 0.15 molar concentration given to you. It is only 3% dissociate. Calculate Ka. Now, if you notice, the pattern of the question is more or less the same. It plays around with the percent of dissociation, it plays around with pH, concentration, Ka. Okay, so knowing other values, you can solve the other one asked from you. Okay, in this case, which you are told to calculate Ka. Again, write the expression, okay, when weak acid dissociate, so it become H plus and also A minus. Put it in the ice table. So initial concentration given to you, okay, and you are given percent of ionization. Go back to the formula of percent ionization is initial over original times 100. You get 3%. So you play around with that formula, you should be able to find the H plus at equilibrium. So in this case, it's 4.5 times 10 negative 3 molar. Substitute this into the Ka expression here. Okay, we know the original concentration. We have solved H plus. We can solve Ka. So in this case, 1.39 times 10 power negative 4. Alright. For example 7, I want you to do it as your exercise, okay, and for your attendance. So upload a picture of your solving step to this question, okay, in the link provided. When acid or base is added, this change. When this change means the concentration would change, and you have to find the new concentration. Okay, this is the original concentration. This would be the new concentration after the addition of strong base or strong acid.